So last time we looked at how you can solve exponential equations when you can write both of the base numbers as powers of the same thing. Okay, so whenever that happens, you can do it without a calculator and it's pretty easy to solve. Today we're going to look at when you can't write them. So 5 and 18, you can't write those as powers of the same base number. Okay, so this is where your calculator is going to come into play. So if you can't do that, then you have two different options for how you can solve these, and it's really kind of a preference thing. So you can either take the log of both sides, or you can change the equation into logarithmic form. Either way, you're going to get to the right answer, okay? So let's take a look at this. So option number one to solve this one, taking the log of both sides. So I would take the log of both sides, and I get log of 5 to the x equals log of 18. Okay, I can drop that x to the front using one of our properties. Right, and then to get the x by itself, I divide both sides by log of 15, right? So we get x equals the log of 18 divided by the log of 5, which I can then go to my calculator and type in log of 18 divided by log of 5. There's a button right off here on the side that says log. That's the one you want. Okay, and we get this number, and we're going to round this to 3 decimal places. So it's going to be x equals 1 point, right? I want 3 decimal places, so I'm going to take the 8 to round the 5 up to a 6. So it'll be 1.796. Okay, so that is kind of your first option for how you could do this. Okay, now you could have also, I took the log of 10 of both sides, log base 10 of both sides. Okay, you could have also taken log base 5 of both sides. Okay, so another option, let me show you really quick, right, is we could have taken log base 5 of both sides. And if we'd done that, then I would have had log base 5 of 5 to the x equals log base 5 of 18. This would cancel out, leaving you with just x equals log base 5 of 18. Okay, and then from there, we'll talk about how you can possibly put that in your calculator. Not all calculators have a way to type in logs like this. The log button on your calculator by default is base 10, okay? So we'll talk about that in just a second, but that's another option that you could have done, okay? All right, so then from there, the other thing that you could do, take the log of both sides, either using base 10 and solve it out this way, or using the matching base of whatever you're trying to get rid of, and then putting that in your calculator. Your other option is change the equation into log form, so just kind of converting. Okay, remember at the very beginning of all this mess, I said converting is going to be the most powerful skill? Yep, it is. So if we convert this, right, all the people in the log cabin, the little number becomes the big number, so that's the 5. The stuff in the middle wanted to be left alone, so the 18, right? Number on the outside wanted a friend. So you can see that by converting, we get to the same place we did if we'd taken the log base 5 of both sides. Okay, great. So now we got to figure out how to put that in our calculator. So depends on what calculator you have. All right, and you kind of just have to check and see. If you have one of the newer calculators, you probably have this option, and if not, you don't. So when you go to the math menu, so push the math button off to the side, you want to go all the way down to the bottom. I'm going to go up instead of down. So depending on what operating system you have, you can see on this one that I have an option that says a log base, but on this calculator, I don't have that option. Okay, so on this calculator, you can't do this. You got to kind of use a workaround. But on this calculator, you can use that log base, and you'll see that there's a spot there that you can type in the 5 and the 18 and get the same answer that we got before. Okay, if you do have that button, chances are you can also use, if you use the window button, but use alpha. So it's F2 is what we're accessing. So if you use alpha and then the window button, it brings up some different options for you, and you can see there's a log base there as well. So you could have also done it that way. Okay, so that's kind of your option. So what do you do if you have this calculator and you need to type that in? So if you have this calculator and you need to type it in, you don't have that log base option, then what you want to do is in your calculator, you need to do the log of whatever the larger font number is, whatever the argument is, divided by the log of the base number. So the same thing that we got here. Okay, so personally, if it were me, right? If you don't think you're going to be able to remember how to put that in your calculator and you don't have a calculator that'll do it for you, I might go this way. It looks like more work, but it's really not bad. All right, all that for one example. So let's take a look at this example. All right, so this guy, if I was going to take the log of both sides, right? So I would make it the log of 4 to the x plus 5 equals the log of 12. Right, I'm going to drop this guy down. So it'll be x plus 5 times the log of 4 equals the log of 12. Divide both sides by the log of 4, right? Don't distribute there. That's going to make it harder. So divide both sides by the log of 4. So x plus 5 equals log of 12 over log of 4. And then from there, I can go to my calculator. So log of 12 divided by log of 4. And then obviously, I'm going to have to subtract 5 from both sides. So minus 5. So x equals negative 3.208. Okay, so that's how I would approach that one. Now, quick side note, when you have an expression like this, okay, please note that the log of 12 divided by the log of 4 is not the same thing as the log of 12 divided by 4. Okay, so those are two very different things, right? This guy, we have a property that says that that is the log of 12 minus the log of 4, right? Not log of 12 divided by log of 4. So be really careful that you don't try to make that combination. It doesn't work that way. All right, and then if we had done this one the other way, so if we'd done this one by converting instead, right? The little number becomes the big number, the stuff in the middle wanted to be left alone, and there's the stuff on the outside. So we're basically here if you can remember how to do this in your calculator. Okay, so if you either have that button in your calculator that lets you type this in, great. And if not, if you can remember to do log of 12 divided by log of 4, that'll get you there. But either way, you're going to get the same answer. Okay, next guy down here. So this one, we got to start by isolating our exponent. So I'm going to start by dividing by 7. And for right now, I'm going to leave that as 12 over 7. Okay, I don't want to get a decimal there because then I'm going to have to round it, and you want to avoid rounding for as long as you can. Okay, so I'm going to take the log of both sides, and I'm going to drop that exponent as I take the log of it. So I'm going to kind of skip a step there. So it'll be x minus 1 times the log of 3 equals the log of 12 over 7. So then x minus 1 equals the log of 12 over 7 divided by the log of 3. Right, so calculator, log of 12 over 7, make sure you close your parentheses, divided by log of 3. And then, of course, we're going to have to add 1 to that. So it'll be 1.491. Okay, if you were going to do the converting route, your first step would stay the same. So you'd still do that same first step to get to here. And then from there, right, little number becomes the big number. Stuff on the outside wants a friend. Stuff in the middle wants to be left alone. Throw that in your calculator and then add the 1 to both sides, and there you go. All right, this guy. So first step, divide everything by 5. So I'm going to get 3.7 to the x minus 2 equals whatever 14.5 divided by 5 is. Okay, I'm going to take the log of both sides. So dropping that exponent at the same time. Okay. Divide both sides by that. So I'm going to have log of 14.5 over 5 divided by the log of 3.7. Okay, and then I'm going to my lovely calculator. So log of 14.5 divided by 5 divided by the log of 3.7. Make sure you watch out for your parentheses. And then, of course, I'll add 2 to that, and it's 2.814. Okay, so kind of as you can see, this is sort of my default method of solving. But again, you could just take it the converting route and do it that way. All right, and then this guy, right? So start by dividing by 2. And the difference with this one is that because this is an e, I don't want to take the log of both sides. I want to take the ln of both sides. So it's going to be the ln of e to the x plus 1 equals the ln of 5 over 2. And the ln of e, remember there's a default, it's a log base e, right? This cancels. So that's just x plus 1 equals the ln of 5 over 2. Your ln button is right below your log button. Everybody's just going to use that no matter what kind of operating system you have on your calculator. And then we'll subtract the 1. So x is going to equal negative 0.084. And there we go. Okay, so that is how you solve log equations. Depending on what kind of calculator you have different buttons that you can use. If you have the kind of calculator where you have the option in your operating system to do a log base like that, then you're probably better off trying to just convert and go that direction. If you don't have this, I would recommend you go this way, okay? Because trying to make sure you remember that rule, the rule about how to put that in your calculator, I think is a little bit trickier than doing the extra steps. But it's a preference. You can do whichever. All right, so the second thing I want to look at down here is something called Newton's law of cooling. So this is something you may have run across in a science class before, but it's basically a law about things that cool down, figured out by Newton, so hence the name. So we got this lovely formula, okay? So U of t, that's function notation. So it's saying that we're finding U, right? So U of t is the temperature of an object at a certain time, right? So lowercase t is time. So we're finding U is basically your temperature. So U is your temperature at any given time t, okay? Capital T is the surrounding temperature of the thing, okay? U sub 0, I don't know why that's capitalized, it shouldn't be. So U sub 0 is your initial temperature of the object. Remember how when we did it at the beginning of the year, we had V naught and we had the other one, H naught, that was it, for our initial height and our initial velocity. Same thing, U naught is the initial temperature, okay? K is your rate of cooling for a particular object, and T is time in minutes. So let's break this down. So the idea here, right, and I guess let's look at this word problem. So we have a pizza, it's pulled out of an oven, the temperature of the room around it, and then after 5 minutes, we know how the temperature is. We want to figure out how long do you need to wait to eat it to hit a certain temperature, okay? So basically, if you think about kind of what happens as you have hot items and they're in an area where they're cooling down, right? If you take a cup of coffee and you walk outside with it on a 90-degree day, so a hot cup of coffee, 90-degree day, it's going to take a lot longer for that coffee to cool down than if you walk outside with a hot coffee on a negative 10-degree day. Right? It's obviously going to cool faster depending on the temperature around the item. So depending on the outside temperature, the thing will cool faster or slower. Okay? So that is one of the things that matters. So the temperature surrounding the object makes a difference. Okay, but the other thing that makes a difference is what the item is made of. Okay, like metal versus water. One of those is going to cool much faster than the other one. So what this K is every particular object has a rate at which it cools. Okay, so you find like this default rate based on just testing it and seeing what happens to figure out for this particular item, what is its rate of cooling. Okay, and then obviously time factors in. Okay, so we're kind of looking at that, and those are the things that we're looking at. And you can sort of see here, there's some dregs that sort of feel like, remember our exponential equations where we had, minus r raised to the rt and stuff? There's sort of some hints of that in here. It's not quite the same. Okay, so let's take a look at this problem. So we got this pizza. We know its temperature being pulled out of the oven, right? So that right there is the initial temperature of the object. So when you first pull it out of the oven, this is how hot it is. So that's U naught. All right, it's removed at 5 o'clock, and it's a room that's a constant 70 degrees. So T, that's the surrounding temperature. So this is capital T. All right, after 5 minutes, it's at 300 degrees. So this is our time. That's lowercase t. and it's at 300 degrees now. So that is the new temperature of the atom, right? This is the temperature of the object at a particular time, 5 minutes. So this guy right here is U of T. Okay, so then what they're actually asking us to find is they're saying, okay, well, we want to eat it when it's at 135 degrees. So we want it to cool down now even longer. And so we want to know how much longer do we need to wait to eat it. So what we're going to do is we're going to use all of these numbers we've looked at so far, right? The only thing that we're missing is K, right? We have U of T, we have T, we have U naught, we have little t, we don't have K. So what we're going to do is we're going to use these 4 numbers here to figure out what is the rate of cooling for this particular pizza. And then once we know that, then we can turn around and say, okay, now let me use that to calculate this next part of the problem. Okay, so this is going to be sort of a 2-part problem. Okay, so part 1 is we need to find K. So I'm going to use all this information. I'm going to plug it into this equation. So U of T, that's 300, equals capital T, 70, plus U naught, the initial temperature, that was 450, minus capital T again. So that 70 is going to show up a couple of different places. There's our good friend E. K is the thing I'm looking for. And then lowercase t is your time. So that's 5 minutes. Okay, lovely. And now we need to solve this equation. Okay, so first thing I'm going to do, right, I'm going to actually do 2 things at the same time. 1, I'm going to subtract the 70 from both sides. And 2, I'm just going to simplify my parentheses. Okay, so 70 subtracted from both sides, that's going to be 230. Okay, and then 450 minus 70 is 380, right, times e to the 5k. I'm going to write it as. Okay, now notice, right, this is being multiplied by e. It's not inside of the parentheses with e. Okay, so this isn't being raised to an exponent. This is just a number in front. So next I'm going to divide both sides by that 380. So I'm going to do 230 and divide that by 380, right? And that equals e to the 5k, and it works out to about 0.605-ish. And then from here, we're going to solve this equation. So you could either think about it as converting or take a log of both sides. But since we have e as our base number, I want to take an ln of both sides. So I'm going to get the ln of this 0.605 equals, right, ln of e to the 5k. And the ln of e cancels, so that's just 5k. And then I can solve this pretty easily. So I'm going to go back to my calculator, taking the ln of that previous answer and dividing it by 5. Okay, and that right there, that is our k value. So that is negative 0.1004 I'm going to go with. Okay, so there's our k value. Now, we have not actually answered the question yet, right? Because the question didn't ask us what's the k value. The question asked us, if we want it to be at 135, how long do you need to wait? Okay, so now that we know this, now we can go back and do the second part of our problem. So step number 2, okay, is now we're going to find, right, t. So find the time. How long do you have to wait to eat it? When our new temperature, right, that's u of t, is 135. All right. And I'm going to take this time to show you a cool trick on your calculator that you can do. All right, so there's this thing that you can do on your calculator when we have a number like this that we want to use and we want to kind of like hang on to it and use it later. There's a feature in your calculator that you can use. So see this button down here that says STO? That stands for store, like you're going to store this number. So what I'm going to do is I'm going to hit that button. You'll see the little arrow, and it's saying take that answer and we're going to put it into one of these letters. You know those letters that match your alpha button that you've always looked at and you've used to type messages to your friends, right? Okay, well, that's what we're going to use. So I'm going to go ahead and use K. That's the one above the parenthesis. So I'm going to say alpha and the parenthesis to get a K there. And I'm going to hit enter, and you're just going to see that number show up. And now what's going to happen is anytime you enter that number K, it's going to record it as that number. Okay, that's why if you've ever tried to like solve an equation and typed in like 3 and then used the X button down here, that's why you get an answer when you do that, because there's a default number stored in there and that's what screws you up. Okay, so I just stored that K number. It's going to be kind of handy. You don't really have to do that. If you're careful about it, you could always just kind of go back to your previous answers in your calculator and use those. But I don't know, I think it's kind of cool. And it's really handy in some situations. Okay, so now I'm going back to this equation. So U of T, my new temperature that I'm looking for is 135. The surrounding temperature is still 70. My initial temperature is still 450 degrees. Oops, didn't mean to close those yet. Minus the surrounding temperature. And then it's E, but now we know K, it's about that 0.1 or negative 0.1, right? And we're multiplying that by T, which is what we're looking for. Cool, so now I'm gonna go ahead and solve this. So again, subtract the 70 from both sides, that's 65. And I can combine those numbers, that's still 380. And it's E to this negative 0.1 T. Divide both sides by 380. So I'm just gonna call it 65 over 380 for now. Okay, like before, I'm going to take the ln of both sides. So it'll be the ln of 65 over 380 equals, and then the ln of E is going to cancel and leave me with negative 0.1 T. So then I'll divide that by that K. And remember, that's my K value, right? That negative 0.1. It's not just negative 0.1, it's all this nonsense. So what I'm going to type in my calculator now, sorry, I'm trying to set this up so you can see it. There we go. Okay, so what I'm typing in my calculator is I'm doing ln of 65 divided by 380. And then I want to divide that, and I'm going to use alpha K. And that is my answer. So my T is going to be about 17.6. So the question is, how long do you need to wait to eat your pizza until to get it to drop from 450 degrees to 135 degrees. So you need to wait 17.6 minutes. Okay, so it's kind of a two-part question. You got to figure out what your K is, and then you go from there. Okay, so this is a pretty cool thing. It's something that you could use. Obviously, you could use it in food science if that's like your thing. But on a more macabre sort of note, this is what like CSI, like crime scene investigators do. When you find like a dead body and you're trying to figure out how long has the person been dead, right? Is you can use some of these measurements to figure out, okay, well, we can estimate this is what the time of death is. So if you've ever wondered, how do they kind of figure that out when you find somebody that's dead? How do you figure out when they died? This is sort of the idea, is that you can look at how much residual heat is left in their body and use that to figure it out. So it's kind of a cool thing, very useful in a practical world situation. Okay, so that is how you solve exponential equations using a calculator and how you use Newton's law of cooling.